Hey everybody, welcome back to another video. And yeah, we're just going to discuss a little bit of matrix multiplication. So if you're comfortable with matrices and the manipulation of matrices, feel free to go ahead and skip on to the next video. Those of you that feel like you just need a little bit more review, stay tuned and we'll try to get you cleared away for the next one. Any case, so we're moving through the topic of linear algebra, and one of the things that comes up very quickly in linear algebra are these ideas of matrices. Matrices. Okay. Now, we could probably go into loads of depth and that kind of thing. What I'll say is that matrices are a convenient way for storing information in a compact form. Okay. So in some sense, I think of this as storing information. Storing information compactly. Or you could put in here, physicists and mathematicians are lazy. And that's really what it is. So let me give you an idea about the structure of a matrix, number one. Then how do we actually go through and multiply matrices together? That's the second thing. And then either we'll talk about some utility for a matrix or we'll just simply go on to the next video. I haven't quite made up my mind on that one yet. So here we go. So the first thing that we should discuss about matrices are their size. Size, question mark. Okay. And a matrix itself is an array of numbers. So if we want to write a matrix, we'll call it matrix A for a moment. What we'll do is that we write a bunch of numbers. And so I'll call this lowercase 1, 1, and then lowercase 1, 2, dot, 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 and then lowercase a, 1, and we'll call this m. Okay. In other words, you have some sort of array, some sort of numbers written out, and we generally do this labeling procedure, 1, 2, 2, 2, dot, 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 and we'll call it A2M. So you notice that I've written going along here, we start out at 1 and we go to M entries. In other words, there are M columns. And then as we go down, we change the first entry, the index of the first entry. And so we'll go dot, 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 and we'll go AN1, AN2, and then dot, 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 ANM. So we have M rows and we have N columns. So strike that, flip it.
We have to get on, we have so much time and so little to do. Strike that, reverse it. This way, please.
We have M columns, as I've written, and we have N rows. So in total, we have M times N entries. Right, we have M columns, we have N rows, and that means that if we multiply the two, we have M times N entries. Okay. Now, how we specify entries, as you've already seen up here, is that each entry is given an index. And these subscripted numbers here is what I would refer to as an index. And so the first index represents the row that it is located in, and the second one indicates the column. So when I write A, lowercase, I'm writing the row number, the specific row, and then the specific column. Okay. Now, usually you can call this an entry, but more often it's called an element. So these are just some definition terms, if you will. So what we would say is because of it having N rows and M columns, we would refer to matrix A as being an n by m matrix. So we always refer to the row as the first one and the column as the second. So A is an n by m matrix. Okay. Good. Now this, of course, can be, I say it's storing information. And we'll have to give you some ideas of what these are, but generally every element is a number. So that's the first thing, is just giving you an idea about how do we specify the size of a matrix, and giving you an idea about how to specify elements inside a matrix. So now let's go ahead and get an idea about matrix multiplication. So we need two matrices. I will use a 2 by 3 matrix. So let's say that A is a 2 by 3 matrix. A is 2 by 3. So and I'm just randomly pulling numbers here. So I'll just call it 1, 2, 3. So 2 rows and 3 columns, and we'll call it 4, 5, and 6. And while we're at it, we'll call B a 3 by 2 matrix. So go ahead, write down a 3 by 2 matrix for B. And you can use the same numbers. Okay. So a 3 by 2, so 3 rows and 2 columns. So, okay, 3 rows. So I need to go, I'll go 1, 2, 3, 4, 5, 6. There we go. Okay. So I've got 2 matrices now, and it's not by accident that I've chosen these sizes. Okay. These will allow us to actually perform matrix multiplication. Okay. So the first thing is, let's go ahead and I'll write, we would like to multiply matrix A by matrix B. So multiplying the two together. What does this look like? Well, I will first write down matrix A. So I'll write 1, 2, 3, 4, 5, 6. And then matrix B. 1, 2, 3, 4, 5, and 6. And the question is, what is the result going to be? I will highlight as well that this is a 2 by 3 matrix and a 3 by 2 matrix. So I'm writing down the sizes here. Okay. Now, how matrix multiplication works is that you take each row of the first matrix and you multiply by each column of the second. And depending on which row and which column, that determines the element of the resulting matrix. So what I mean by that is, if you take the first row and multiply by the first column, that gives you the 1, 1 element of the resultant matrix. Or if you take the second row and the first column, that gives you the 2, 1 element of the resulting matrix. Okay. So it's that whichever row and whichever column that dictates the location of the final element. So that's the first thing. Okay. Oh, yeah, that's a good question. Let me ask you this. So based on that, okay, the row of the first matrix and the column of the second matrix dictates the element position. Okay, so based on that, what's the final size of the resultant matrix? Okay. Well, the rows of the first matrix and it's the columns of the second matrix. So the resultant matrix is going to be a 2 by 2 matrix, right? Because the first matrix has 2 rows, the second one has 2 columns. So the resultant is going to be a 2 by 2. Now, how do we actually calculate the values of the elements? Okay. So how this works is that we multiply, so say we're doing the 1, 1 row. Okay. What we are going to do is multiply each column element by each row element. What do I mean by that? Well, we're going to take the first column of the matrix A and multiply by the first row of matrix B. So I have 1 times 1 here. And we're not done yet, though. We have to do it for all 3. So I have 2 times 3. And I have 3 times 5. And at the end, we add them all together. So we go across the columns of A, we go down the rows of B, multiplying each element together, and then we take the sum at the end. Frankly, this should feel, and it's not by accident, a lot like a dot product. You're taking 1, 2, 3, if you will, and you're dotting it into what we'd call the column vector 1, 3, 5. So multiply the elements and then take the summation. So we could continue doing that. That's the, since we use the first row and the first column, that is the 1, 1 entry. And you see right away we're going to run out a lot of space. We're going to have, probably need more space here. Go ahead. Okay, that was the first entry. Go ahead and do the rest of them. Do the other 3 entries. You got it? Good, good, good. So I'll go ahead. So the second one, let's use the first row and the second column. So we have something like 1 times 2 plus 2 times 4 plus 3 times 6. Okay. And we go ahead. Now we have to use the second row and the first column. So I'm on the second row now in the first column. So we have 4 times 1 plus 5 times 3 plus 6 times 5. And lastly, we have the second row and the second column. So we have 4 times 2 plus 5 times 4 plus 6 times 6. And again, as promised, we have a 2 by 2 matrix. Of course, we can simplify this. Let's go ahead. 1 plus 6, 7, plus 15, so this is 22. 2 plus 8, so that's 10, plus 18, so this is what, 28? You'll have to correct me if I'm wrong. Of course, you're probably screaming and saying, no, 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 that's... Yeah, okay, we're fine. Probably screaming at the screen. 4 plus 15 is 19, plus 30, so this is 49. And last but not least, we have 8, 28, plus 36. So 28 plus 36 is 44, 64. And there we are. Here is our resultant matrix that arises from multiplying A times B. Okay. So right now I'm not really giving you an idea about where these matrices come from or what does this final resultant mean. We're just going through kind of mechanically how do we multiply the two matrices. So I'm not worried about what does this result mean right now. Okay. Go ahead. Okay. So the next question for you, what is B times A? So number one, does B times A give you the same thing? Number two, if not, what is B times A? Both in terms of size and actual numbers. Go ahead, ask yourself, does B times A give me the same thing? In other words, is matrix multiplication commutative? If not, then the second question is, what's the size of B times A? And what are the element values? Go ahead, take a minute, think about that. Good, you back? Hopefully you see that B times A does not equal A times B. In other words, when we're performing matrix multiplication, the order matters. It is not commutative. Okay. Does not commute. Can't emphasize that enough. So we have to be careful. And we can actually see that if we look at the sizes of B and A. So when we did A times B, now I'm thinking about sizes here for a moment. A was a 2 by 3 matrix. B, as in boy, was a 3 times 2 by 2 matrix. And you notice that the resultant was a 2 by 2. How about if we do B times A and we think about the sizes for a moment? Well, B is a 3 by 2 matrix. A is a 2 by 3 matrix. And so what do you think the resulting matrix size is going to be? Yeah, the resultant has the same number of rows as B and the same number of columns as A. So you get a 3 by 3 matrix. So clearly you don't end up with the same thing. They're not even the same sizes. And that's the general rule. Notice, in order to do matrix multiplication, the columns of the first matrix have to equal the rows of the second. So I'll write this down. In order to multiply columns of first matrix, if I could spell, must equal the rows, say number rows of second matrix. And that should make some sense when we think about how we performed the multiplication procedure. Remember, we went across a row of the first matrix. In other words, we counted up the number of columns, and we went down the rows of the second. So we went across the columns of the first and down the rows of the second. If those two numbers don't match, then at some point you're supposed to multiply an element by, I can't say 0, but you're supposed to multiply an element by nothing. Not 0, right? 0 is a number. I mean nothing. Well, how do you do that? That's not possible. You can't multiply a number by nothing. And that doesn't make any sense. So this is the general trend, is that when you want to multiply two matrices, you have to make sure that the columns of the first matrix matches the rows of the second. And then the unused ones, if you will, the rows of the first and the columns of the second dictate the size of your final matrix. Okay? Go ahead. Okay? Find hopefully you've done the multiplication, but if not, pause the video right now and go ahead and find the actual multiplication for the numbers that we have. You got it? Good, good. Now, I'll be perfectly honest. When I have to do matrix multiplication, I usually have to write it out. Okay, I'm not good enough to think about it in my head. I usually have to write it out so that I can see what I'm doing. So there's no shame in that. Don't try to shortcut it. It just takes a while. Okay, so I'm going across this row. So I have 1, and I'm going down the first column. So I have 1 times 1 plus 2 times 4. That is my 1, 1 entry. Well, now I have to go across and go down my second column. So that's my first row, second column entry. And I have 1 times 2 plus 2 times 5. Rinse, wash, and repeat. First row, third column. So I have 1 times 3 plus 2 times 6. And now we're done with that first row. Now we've got to go down the second row. So I move down 1 on the resultant matrix. I have 3 times 1 plus 4 times 4. And we just rinse, wash, and repeat. 3 times 2 plus 4 times 5. 3 times 3 plus 4 times 6. You can kind of start seeing the pattern, right? So this first column, it's always 1 and 4 that I'm multiplying by. So we'll go ahead. Last row, 5 and 6. So I have 5 times 1 plus 6 times 4. 5 times 2 plus 6 times 5. 5 times 3 plus 6 times 6. And there we have it. We have our resultant matrix, a 3 by 3 matrix. And we'll go ahead, and of course, if you want, you can simplify this whole rigmarole. I don't know if that's necessary or, okay, well, we'll do it real fast just for completeness. Boom. There's our final answer. Da-da-da-da. Pretty cool, huh? Okay. So you say, well, how does this help me? Okay. First off, like I said, we need to think about matrix multiplication. How do matrices actually multiply? How can I write out, how can I use that to simplify my expressions? Okay. So that's the big thing is, do you understand the matrix multiplication? And actually, for the last byline, you've been doing matrix multiplication. I've already hinted at it. Anytime you do a dot product, you're doing matrix multiplication, right? Let's say, for example, that you're trying to calculate the work being done as you push a box across the floor. Call this delta R, F. Okay. What would you do? Well, to calculate the work, you would do something like an integral of F dotted into the displacement dr. Okay. Now you call this a vector. We call this a vector and this a vector, right? And I should ask, how many components, how many elements do each of these vectors have? 3. Okay. The dot product is multiplying a vector force, a 1 by 3 matrix multiplied by a 3 by 1 matrix. Okay. That's how we set up the dot product. And you notice that the 3 columns of the first matrix and the 3 rows of the second matrix. And so our resultant matrix, if you will be a 1 by 1. Now, generally, we don't call that a matrix anymore. We call that a scalar. You only need one index to specify which element you're talking about. Because it's a 1 by 1 matrix, actually, technically, I guess you only need 0 indices. There's only one entry, so you need 0 indices to specify which element you're talking about. If we return to these vectors for a moment, you notice that this has 1 row and 3 columns. So we generally refer to this as a row vector. And we would generally refer to this one as a column vector. If we were actually to write out these things, you would have something like 1 row and 3 columns. So you'd have the X component, you would have the Y component, you would have the Z components. And you would multiply this by the X component of the displacement, the Y component of the displacement, the Z component of the displacement. And you would end up with, right, the X component times the X component plus the Y component times the Y component plus the Z component times the Z component. Pretty sneaky, right? You've actually been doing a small version of this matrix multiplication when you apply the dot product. For completeness, okay, now you can turn it off. Like if you're say, okay, I've got this matrix multiplication, I'm done. Okay. For completeness, since I've gone down that rabbit hole, a number that requires 0 indices is what we refer to as a scalar. If it requires 1 index, you already know what we call that. A vector. Right?
Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
I've done it actually right here. You only need 1 index to specify what you're talking about. Right? If I want the second component, okay, or if I want the third component or the first component. So if it only needs 1 index, it's what we call a vector. That's usually what we would refer to in physics. 2 indices, I'll say 2 plus indices, you'll see 2 terms. You'll either see it called a matrix, or sometimes you might see it called a tensor. And it depends, a lot depends on which field you see it in. Generally, when I see it in physics, it's going to be called a tensor. And you'll see these pop up in mathematics and engineering as well. Engineering and physics will call it a tensor. Mathematicians tend to call them matrices, or they might use a term called an array. Array might be a mathematician or a computer scientist. So it depends on which field you're in. I'm just giving you kind of, for completeness, some of the terminology you might see. So that's all I have for matrix multiplication at the moment. But next lesson, we're going to take those system of 3 equations that we saw in the previous lecture. We're going to apply this idea of matrix multiplication in order to write those 3 equations more compactly. And then we're going to get some ideas about how do we do the math faster. Thanks for your attention. I'll see you next time.